And hello everyone, welcome. And welcome to this video on Turbulence Modelling. We're going to continue discussing our case structure for our OpenFOAM example. So in the last video, we were talking about, hey, this last cell is determined by whichever cell has the greater x coordinate, right? So yeah, that's pretty much the idea. And the ratio, if you give it an expansion ratio, and what we saw in the last video is that this expansion ratio in the x direction is 1. Then the x coordinate, or rather the ratio of the sizes of the last cell and the first cell will just be 1. There's no expansion there. Now what happens if you have a y coordinate? So see now the y coordinate, for the y side, the expansion ratio is like something like 10.728. So 10.728, it will be equals to L last over L first. Now where's the first and last cell? And this is in the y direction. So if let's say you have a y direction like this, so your first cell will be at the lower y direction, and your last cell will be at the larger y coordinate. So this is your first cell, this is your last cell. Alright, and this is so-called for one side. Now of course, if you have your whole domain where this is like the wall, and then you have a wall on the other side, you have to kind of stop halfway, right? Because you want your cell size to be small near the wall, you want your cell size to be big over here. So as you increase y in the second part, your cell size should be smaller. So your last cell should be 0 point something times of the first cell. So this is what you are seeing here. Your last cell is actually 0.0934 times of the first cell in the second block. So the second block has coarser mesh here, finer mesh near the wall. The first block has finer mesh near the wall and coarser mesh here. So that's the idea of what we are doing with this simple grading. Hopefully that clarifies things. If there's not too much else here, so just gonna continue. Interesting things, just wanted you to take note. We use the type wall for these boundaries. Yeah, we use type wall. The type is called wall because I mean we still want to activate our wall functions if ever we want to use this what do you call that? We use the turbulence models and like a RAN simulation or whatnot on this. Then we want to kind of have, you know, a wall, like this. I mean the patch is named a wall, so that we OpenFOAM recognize, oh, this is a wall, I need to use a wall function, and that'll be okay. The rest are pretty simple. They are just cyclic. Now this cyclic is pretty simple. This is a periodic boundary condition. What is periodic boundary condition? Remember we said that we want this channel, okay, this channel, this kind of channel to be infinite. So alright, if you have velocity coming in here, it will go all the way to, let's say you go to the right, and then when the fluid goes into here, where does this velocity, where does the fluid go? Basically, a periodic boundary condition just recycles the fluid to here. So whenever you see, you know, something that is saying cyclic, like you see here, this is the periodic boundary condition. Now how do you tell OpenFOAM which two surfaces to, you know, connect together? You specify it with this thing called neighbor patch. So this side's half 0 is actually connected periodically to this side's half 1, because the neighbor patch here of sides half 0 is actually sides 1 half 1, which is this patch, and this patch should also have the neighbor patch saying sides 1 half 0. So both of them should reference each other as the neighboring patch. So neighboring patch is the one that, you know, they have this whole cycle, the periodic boundary condition that links them together. Alright, so these two are linked. Okay, and apparently for inlet and outlets, they are also all cyclic boundary conditions, which is basically a periodic boundary condition. So that is pretty much how you set up a channel case using block mesh. Okay, so that settles the block mesh bit. Now, of course, you need your boundary conditions. So for starters, we can take a look at the UP and etc. boundary condition. We actually go to 0, all right, and we take a look at, for example, p.gz. Okay, this is the full case. They give you an initial field. So, so this is what the boundary conditions are like. If you scroll all the way to the bottom from, let's say, you know, these are actually values, individual values of the cells. Okay, so at the walls, the pressure is normally considered 0 gradient. Okay, and the rest of the way you have cyclic boundary conditions. So you just say that the type is cyclic, then OpenFOAM recognize, hey, this is a cyclic patch. This is a periodic boundary condition. So that's for pressure. For U, okay, for U it's the same. Okay, then okay, so bottom wall is a fixed value. This is a no slip condition, right? It's a fixed no slip condition. Hopefully you're familiar with that by now. Here, all the rest of them are also cyclic. So thing is this, if all of these are cyclic, where does the driving force for velocity come from? So you won't find it here in the boundary conditions like you normally would set up a pressure difference or something to, you know, have your velocity flow or whatnot. There's a different way to do it. Okay, but before that, I'll just take you through the new T, which is turbulence viscosity. Again, all of these are very similar, 0 gradient and cyclic for all the periodic patches. For the walls, it is 0 gradient. Okay, for the walls, it is 0 gradient. And for how do we get this driving force? Actually, there's a very special function that you go to FV options, and then it'll give you this thing called the mean velocity force. What does this do? Now this actually gives you a driving force such that the average velocity, and this in the X, Y, and Z direction is what you specify over here. So this momentum source, so to speak, using this mean velocity force, it will give you it will give you the driving force you need for your velocity. So no need to worry about them, setting them right in the boundary conditions. So this is very, very useful because especially for channel flow, especially all the case has been set up as such already, so you don't really need to do anything too new. Okay, so this is the boundary condition. Okay, in a thermal and a constant directory, instead of transport properties for, let's say, pimple foam, we need to use thermal physical properties for buoyant pimple foam, and that is based on my heat transfer case in hot sphere in oil. I'll just use some transport properties on thermal physical properties for oil, Daltherm specifically. So yeah, and what about for turbulence properties? Okay, turbulence properties, I mean, in this case, it is a whale model, more adapting local additive viscosity. You can specify it to be IDDES or RANS, whatever. I'm not going to say how here, but what about for DNS? DNS, we do not have any turbulence model, so simulation type, you can treat it as if it's a laminar flow. So you can say it's a laminar flow here. What it means is that it'll turn the turbulence modeling off, but it's not. It does not mean that the flow is laminar. It just means that there's no what do you call that? There's no turbulence that you're simulating with a model. So everything is resolved in a DNS. Okay, so let's move on. Okay, so these are some of the important things we need to do. Of course, there are other fields like the temperature fields and the gravity, which they are not found here, but where we can take a look at this is the for example, you see buoyant cavity. Okay, buoyant cavity. Alright, you will see that there is a G file here, which means that you need to specify the direction and magnitude of gravity. That's one, because this is for natural convection and heat transfer, so you need to specify these extra fields. For the other fields, you need to specify temperature. Okay, you need to specify the temperature. So I'm going to have very simple. On one hot plate, which is 100 degrees, one cold plate, which is about 40 degrees. So these are fixed temperature. The rest of them will be cyclic. So I'll show you what the things are like later. And of course, you have alpha T, and there will be some wall function there, the turbulent Prandtl number of 0.85. This will only specify the first cell away from the wall, what the heat transfer or whatnot is. Okay, so this is only for the first one. The rest not so important. Of course, if your turbulent viscosity is so small near the wall, doesn't matter what Prandtl number you give, it will always turn out to, the turbulent heat flux will always turn out to 0. Okay, right. So of course here, if you were to use the K epsilon model, these two fields will be important. K omega model, these two fields will be important. Now, one more difference is this PRGH. PRGH is actually okay for buoyant cases. All right. For example, buoyant pimple foam. Normally, what we do is we don't calculate the total pressure. We calculate the for OpenFOAM. Usually, the field that's calculated is the pressure without the hydrostatic component, which is this PRGH, which you see here. So for most of the pressure field, we have this calculated thing here. The rest of them, usually we just have it to be cyclic. All right, so most of the pressure settings you want to put here, all right, in here. And what it says here in this PRGH, we have a fixed flux pressure, which it's slightly different from what we saw just now in the zero gradient. But essentially, this is a zero gradient, but it gives OpenFOAM the capability to adapt for hydrostatic pressure, pressure variations, etc., etc. So this is what fixed flux pressure is. And that's what you can and should use for your boundary conditions. The rest of them are more or less the same. Alright, for these boundary conditions, you use a wall function for alpha, your K and epsilon, they will have certain wall functions as well. So if you take a look at nu T, you have a nu T wall function here, and you look at the K, you have a K wall function here. These things you can just copy and paste. And the rest of them, of course, you have cyclic for the rest of the boundaries. Alright, so these are the boundary conditions. For temperature boundary conditions, we have fixed temperature, zero gradient, I won't say cyclic. Cyclic is more correct. Cyclic on all sides, which means it's periodic. For velocity, we need to fix the mean flow and make it periodic. So we found out how using the fv options in the channel 395 flow. We'll just copy and paste that over. And for pressure boundary condition, we have we need to have some sort of fixed pressure drop to make the flow constant. But that actually comes from the custom fv options that we specify, so we don't really need to worry about this. We just need to make the site cyclic, and the rest of not the sides, the open ends cyclic, and the walls should be the fixed flux pressure. So that's more or less the general idea. Okay, for boundary conditions. Now looking at this, we can look at discretization scheme. The idea for DNS is, or LES for that matter, we want as non-dissipative as possible. So generally speaking, we use a central difference approximation with second order. This will be Gauss linear schemes or Gauss cubic. So we can take a look at some of the discretization schemes, and some of them you can actually find inside BoxTurb. BoxTurb is actually, if you take a look at the OpenFOAM tutorials, CD form tutorials. Okay, I'll show you where to find them. You see this DNS here, so we go to DNS, and that's the only case that you'll find there, box turbulence. And from this you can take a look at what kind of fvSchemes, finite volume discretization schemes you can find. You know what finite volume discretization schemes you can adopt. And what is this finite volume discretization schemes? This one's actually turn all the partial differential equations into a system of matrices, and how those matrices are structured, it depends on your schemes. That means, do you want a central difference approximation or lower order, first order approximation of the gradient, etc., etc. These are what fvSchemes are about. So we can take a look here in the system directory of this BoxTurb, which I also copied here. So BoxTurb 16. Okay, I can look at the fvSchemes. We can look at the fvSchemes in fact, and we see that the DDT schemes, these are time schemes, or use an Euler function. Gradient schemes, we use a Gauss linear. Divergent schemes, where you have this divergence of phi and u, you use this thing called Gauss cubic. And the rest of them we have Gauss linear corrected, blah blah blah. Nothing too worrisome over there. So we can use these settings to try and get ourselves started with the fvSchemes for this custom file that we are working on here. Of course, we will need to look at some other fvSchemes as well, because they don't specify. These things don't specify fvSchemes, right, for the heat, energy related. So for example, fvSchemes here, I'll go into fvSchemes. You see there are lots of turbulence quantities here, and you see this thing phi h. Phi h is actually the convective term for enthalpy. So this actually will need to be decided as well. But of course, we try to use Gauss linear as far as possible, so it should be okay. But other than that, yeah, that's more or less what your fvSchemes are. So you just need to kind of copy and paste some of these schemes, change the entries here from bounded Gauss limited linear to maybe something like Gauss linear or Gauss cubic. So Gauss linear is more or less okay, because you find in the quasi DNS paper, using a second order scheme, it's pretty much good enough, as long as your mesh is small. Now fvSolution, so this one's a little bit more interesting or challenging, so I'll just quickly go through them. Okay, fvSolution, it will tell you what are your tolerances that you need, and of course you may not know what this GAMG or PBICG step is. Those are basically linear solving methods for the matrices. So fvSchemes actually breaks up your differential equations into various various matrices. Breaks up your partial differential equation into a lot of matrix. So fvSolution will say, oh, how do I solve these matrices? So some of the iterative solutions are this generalized algebraic multigrid, GAMG. The basic idea is to take, when you solve your mesh, you try and solve you have a certain mesh level, you have a certain mesh level, and then like this. So what they do to solve is that they make this mesh a little bit more coarse, okay, and they solve the coarse mesh solution. Then they use that as a starting value for the final mesh solution. So that's what GAMG does. Okay, of course on the surface that sounds good. It means that you have very good initial guesses. So I mean, for pressure equations, those are generally okay, but it may slow down. I mean, there's a lot of nuance to which solver to use, and there's a lot to learn in this bit. But as long as the idea here is, of course, stability and speed. That's all you want. Okay, I'll stop for now, and I'll see you guys in the next video. I'll continue discussing all these fvSolutions in some briefly. Okay, thanks for watching.